Hi guys.
Hello everybody.
So, what we are going to talk about today, and why it would be worthwhile for you not to be sleeping during our talk.
Our English is bad.
Today we are revealing the technical details of our vulnerability, showing how we exploited and bypassed internal mitigations. Also, we will disclose several architecture flaws of late Intel ME firmware and emphasize why it is very dangerous making this powerful subsystem with digitally signed firmware. But before this, let us introduce ourselves. I am Mark Yermolov. I am a system programmer. I'm interested in security of hardware, firmware, and low-level system software. Today I'm working at Positive Technologies, researching inner workings of various components in Intel platforms. For example, PCH, IOSF, iGPU.
And my name is Maxim Горячий. I'm also a security researcher and developer at Positive Technologies. Our research team includes the following people: Mark, me, and our colleague Dmitry Sklarov, who also has been presented a research at Black Hat concerning the internal structure of the Intel ME file system. Themselves of some of our previous work we have found on the slide. We will talk today about the Intel ME, how it's implemented, where the researcher can find vulnerability in ME. Then we will disclose in detail how our exploit works and show demos proving our achievements. Intel Management Engine 11 overview. The topic of management engine is very popular now. We think you agree with it. Here is why it's so disturbing. First of all, it's almost fully undocumented and very powerful at the same time. For example, it has full access to your platform's hardware, including CPU complex. It has capability to intercept almost all that you are doing on your PC or laptop. And it tells a root of trust of many modern Intel security technology, like TPM, like BootGuard, like DRAM. Intel has chosen the following design for ME. Independent x86 processor core, our operation system based on Minix, built-in Java machine, and also ME gets started before main CPU. Firmware has parts in PCH Burnit, in memory, and in SPI flash. In this slide, we have listed Intel technologies that we now implemented with the help to management engine. Of course, it is MT active management technology, and PAVP, ACA DRAM, Intel DRAM, PTT, or firmware TPM trusted platform model. And of course, we think that the ME related with software guard extensions or SGX. On the scheme. And let's consider vulnerabilities that are already now to public at the moment. From the moment Intel ME was created, and until now only 3 vulnerabilities were found. The first one was discovered by Invisible Things and presented at Black Hat USA in 2009 in the talk introducing ring -3 rootkits. The next one was AMT provisioning, and the last one, called silent Bob is silent, allowed AMT authentication bypass by a remote attacker. It was very dangerous, but didn't allow executing arbitrary code inside management engine, and was resolved easily. So, until now, there is only one vulnerability that allows executing of arbitrary code. But we found the second vulnerability. Let's talk about how it's possible to impact Intel ME all from the external world and where to find vulnerabilities. We know the following ways to impact Intel ME directly or not. First one, the HE interface. It's interface for local communication between host and management engine. HE is a transport for many services, service protocols used by various models, and there can be errors in parsing of HE data for protocol messages. We think it's very promising vector for future investigation. As part of Intel Security Bulletin, Intel disclosed a local vulnerability that can be used for arbitrary code execution at behalf of AMT. We think it's exploited via the AMT HE protocol. The next vector is network. There is one of the dangerous vector, but in fact, all processors exposing network access have especially loud privileges. So if an attacker exploits the vulnerability, he or she can do anything more than the process allows. The next vector, it's unified memory architecture. Yeah. It seems that now it's useless to attempt attacking UMA because UMA is encrypted now and has an integrity check. UMA is a special region in host memory which ME used such looks like swap for main memory.
Firmware SPI flash layout. Initially, we had an idea to use SPI flash emulator giving different data on subsequent reads of the same address. It could work to inject arbitrary code, but only if module loader reads a code page of module several times, but checks its integrity only once. But in fact, Intel ME engineers have thought about this and protected management engine from such evil SPI flash attacks. The next attack vector is internal flash file system. It is the way actually which we had chosen because we knew that there are many initial configuration data used by ME which are stored into SPI flash in an encrypted plain format. We will not describe the format of internal flash file system now because our colleague has excellent research on this subject presented today at this conference earlier. The next important step is to choose a target module. It is especially important because different processes have different privileges inside management engine. It is where we encounter with Intel ME access control model. Thus, each process in Intel ME has statically defined privileges. For example, whether a process can access particular kernel services or system calls. Also, for each process, its metadata, a special file, hardcodes a list of hardware resources which the process can access. This scheme results in the following architecture problems. The first and most important is that a process can elevate its privileges, spawning new process with high access rights. It is only possible only if a process can create new processes. So it has access to those kernel services. There is only a limited number of processes having access to that system service, and each of them is very suitable for subsequent research. The next problem is that there are some devices, some hardware in Intel ME hardware environment which can be used improperly to bypass Intel ME access control model. One example of such devices is Intel Management Engine static memory controller. It can give access to any physical page of ME static memory. So having in mind these architecture flaws, we can enumerate a list of processes from Intel ME firmware deserving attention. Actually, ROM is first code running on Intel ME. It can everything. RBE is bootloader, kernel itself, and 3 user mode processes. From this, we have selected BUP. Its name stands for Platform Bring Up. Our decision has the following reasons. BUP exists on all platforms, not only vPro systems, but on the desktops, mobile servers. It can create new process system service. Also, it gets started before all other processes and has access as no one else to a large range of hardware resources. We also looked forward for success because of the following. BUP is one of largest modules in Intel ME firmware. Also, it duplicates a lot of other modules' functionality, and it parses a large amount of initial configuration data. And our expectations have been realized. We have found the following function, which we called BUP init trace half, having vulnerability. As you can see, when this function calls another, which we named BUP-DFS get file size, BUP-DFS read file, it gives it incorrect size of data to read. Instead of size of local buffer, the BUP-DFS read file function gets size of whole file. It surely leads to stack buffer overflow if the size of home BUP-CT file is larger than 808 bytes. But it is, what is the magic size of the buffer? How often do you give size to local buffer to that pretty number, 808 bytes? It was perfect for us that this file is not encrypted, not signed, and can be integrated into firmware image by Intel Flash Image Tool utility. As you can see from this listing, it is utility parsing MFS files, internal flash file system, and showing attributes of files. But to successfully load and execute arbitrary code, there is a small problem. The stack guard protection. Intel ME has a classic stack guard called stack cookie or stack canary. It is very simple and reliable. Briefly, if a stack copy of some secret value is changed as it has been detected at function exit, then a stack buffer overflow occurs. So it's time to terminate a process. There is no way to guess or change the initial value of stack cookie because its value is gotten from hardware random number generator and stored in non-volatile process memory. But we have found the way. A first idea was to break hardware of random number generator, so a known value is stored for initial cook value. It was a bad idea because, as we'll later see, operating system kernel loader, if it detects that hardware of random number generator is broken, it stops loading the kernel. So the platform is not booting. And the next idea was to intercept code flow before the change value of cookie is checked. This was a good idea, but very hard to realize. Let's start from code sequences. To explain it, let's start from call sequences that BAP DFS read file function has. As we can see, it calls another function which we named BAP read MFS file. This function actually parses internal flash file system metadata and stores data of files into destination. We can see that to do this function calls another function from system library, syswrite sharing memory. Wait, why does BAP use a shared memory? It doesn't need shared memory. It is only a processor running at that time. It uses only local buffers. The only possible answer for this question is that BAP duplicates functionality of another module, probably storage or VFS. So, also we can see that syswrite shared mem function gets address of destination not from argument, but from some structure which we named shared memory descriptor. This but at scheme. This all but at scheme. Let's go next. So where did? So it turns out that this shared memory descriptor structure comes from another structure, which we named shared syslib context. It is a very large structure containing many control data used by functionality of this system library. One of this data is for shared memory control. So, where did this syslib context structure comes from? It comes from something, as you can see, but this function, it comes from something pointed to by GS0 construction. So the main question now is, what is pointed to by GS0 construction? We found the answer for this question completely reversing engineered kernel module of firmware. And it is nothing else that threat local storage. But what we have found next is a big security flaw of late Intel ME firmware. The thread local storage resides at thread stack bottom, so it is surely rewritable by stack buffer overflow. Let's consider the scheme. We can see our buffer vulnerable, we can see return address of buffer penetrates hub function, and stored value of stack cookie. Also, lower at the stack, you can see the thread local storage, having syslib context pointer. It is not hard to come up with an idea that to overwrite this syslib context pointer with controlled address. So here is what we thought out. There is one major property, important property of implementation of this function, bub read MFS file. It does it iteratively by chunks of 64 bytes. So if it does it iteratively and at each iteration it gets address of destination from some structure which we can control, we get arbitrary write primitive. You can see as a scheme how we rewrite syslib context pointer. Now we make our structures pointing to anything else in address space to write by these functions. But for successfully loading and executing of arbitrary code, there is small problem, another problem, non-executable stack.
And I told about it. It is because stack is not executed because Intel ME operating system implements a strict x86 segmented memory model, and stack segment of process doesn't intersect with its code segment. It means that you mustn't to execute code on the stack by default. To bypass this mitigation, we used a now technique called ROP. We have found all necessary ROP gadgets accessible to BOP for our process creation. It's enough to load and run our arbitrary code. It means that directly we haven't any technique for creation of executable pages. The kernel of management engine doesn't give any syscall for it. You mustn't to create. You can create only data pages from user space. So we used ROP and the previous started architecture flow to be able to load and execute our code models. It means that we create a model, integrated it into SPI flash image of ME, and execute it via our ROP gadgets. And now a little bit of formal description of the vulnerability. As you could see from the official security bulletin for the vulnerability, it has high rating. It's acknowledged that has a local exploitation vector. It affects all recent platforms, desktop, mobile servers manufactured after 2015 years. here are affected Intel platforms. There are hundreds of products manufactured by many vendors based on those processors which are all affected. It is 6, 7, and 8 generation of Intel processor and Xeon processor and Atom and Celeron, of course. Now more detail concerning exploitation vectors. For successful exploitation of the vulnerability, there is conduction. An attacker must have right access to ME region of SPI flash. On a properly configured platform, it is hard. For local attacker, not in case he or she has physical access, of course. If you have physical access, you always rewrite SPI flash via SPI programmer. And also, there are very few completely protected systems. But example, we meet many systems functioning in so-called Intel manufacturing mode. In this mode, you can attacker can send a special HTTP message, and it allows to rewrite ME region. Okay, there are attacker can use vulnerability, of course. Another vulnerability which allows to write into SPI flash. Also, there are problem is settings of ME region in the SPI flash descriptor and processing of the UEFI setup variable in BIOS. We saw it of many platform vendors. Having physical access to the SPI flash, how I said, our platform jumpers makes all those system vulnerability. And the main question, is remote exploitation possible or not? We think it's possible if the system has provisioned Intel AMT and an attacker knows a password to access AMT, or if the system has an AMT vulnerability bypass, such as vulnerability which found in May. Also, a platform is required to have a special settings, a special option in BIOS somewhere called Flash Rewrite Enable. Having this, an attacker can remotely rewrite a SPI region and deploy exploit into ME. It means that attacker, on the first step, attacker connected to target. On the second step, he rewrites SPI region via vulnerability or BIOS option, and after a set of target system, attacker has full access to the platform. Some scope of bad news. Hub is not protected. The special mode hub which we found early doesn't protect against the vulnerability because the exploit works before the model is switched on. It's bad for all consumers of this mode. How we set all vulnerability in BAP
at early stages.
At early stages on BAP, yeah. And the second, Intel firmware update. Actually, the bug can't be fixed completely by any patches because the ME started code doesn't check firmware downgrade. So having local access to the SPI flash, you can always downgrade to vulnerability firmware. It means that you couldn't protect your system against physical vector, for example.
Not from BIOS, as you can see, but local access. So if a measurement engine is functioning as manufacturer mode, you also can downgrade your system to vulnerable version.
And the next bad news, Intel didn't fix the problem with unreliable thread local storage. TLS is still at the same place, on the bottom of the stack. Another stack buffer overflow, and attacker can be use our technique for exploitation.
Stack guard bypass.
For stack guard bypass, yeah. And demo time. The first demo, we show how we activated AMT on non-vPro system. How you can see, system hasn't vPro. It is gigabyte bricks computer.
But client was able to connect the system, as you can see.
Full access via active management technology on system which doesn't support it. Doesn't support AMT. The next video about JTAG. We activated JTAG. It's a debugging technique for engineer on the system.
There is some misunderstanding. People think that we exploit the vulnerability through
via JTAG. It is not true. We activate JTAG via vulnerability. We can step and debugging ME core from reset vector, how you can see.
Here we rebooting Intel ME and it stops at reset vector.
We changed. We will change the value
of HE status.
This register read only for host CPU. We read it, and
it is actually firmware status 0 register. Now we change it.
We change this value, yeah. 1, 2, 3, 4, 5. 6, 7, 8.
So the platforms see new value.
Okay. And the next video.
Hello from Management Engine.
We rewrite GPU images from ME and
at all platform stages in BIOS during loading of operating system.
It's not fake, really.
Microsoft WAG
bypass, new technology. Thank you. And okay, demo. And having arbitrary code execution in BAP model, all those Intel technology based on Intel ME are now in danger. And it means that DRAM danger, firmware TPM. It means that if you use, for example, BitLocker on your Windows host system, attacker can dump your SPI flash, recover FTPM keys, and decrypt your hard disk. Good news. And protection. We believe that maybe Intel will remove it from PCH sometimes. And of course, our achievement. We switched on AMT on non-repro system. How we can see, we activated JTAG for Intel NVIDIA's vulnerability. We dumped static code, ACA-ROM, and also we recovered half-man code via this vulnerability, and you can find this table in our utility on May 11. Thank you, Dmitry Sklarov. And we compromised ME file system because we extracted integrity and confidentiality platform key.
Non-Intel, if you
non-Intel key, non-Intel key. And of course, we bypassed Intel boot guard. We want to say thank you our company, Dmitry Sklarov, Plato Mavropoulos, and other people who haven't helped, but don't want to see their names on the slide. Disclosure timeline, we reported to Intel at June, and Intel fixed it back in November. References. Thank you very much. Question?
Thank you. Have you any questions?
This is on. So projects such as LibreBoot and ME Cleaner aim to disable management engine, but to the best of my knowledge, they don't completely disable management engine. So is the BEP? Have you tested your exploit in CPU which has had ME Cleaner ran and LibreBoot?
Sorry, you mean that how we can use it for disabling management engine, this vulnerability, correct?
Have you tested your exploit against a CPU which has had ME Cleaner ran on it, or a computer which is running LibreBoot, if you are aware of those projects?
How we tested it?
Yes.
Oh, our exploit?
Yeah.
We have two platforms, and we wrote some Python scripts for automatization, some process, and we create ME special create image and deploy it via SPI programmer because it is not problem for us. We don't investigate and real attack vector. We found vulnerability for JTAG activator, for activation JTAG only.
Actually, we have found some way for forward connection with our exploit, but we want to disclose now.
Yeah.
Okay, thanks.
Can I just confirm then that a BIOS password is an effective mitigation against this attack?
For now, there is no effective mitigation of this attack for now.
Sorry.
We hope that this will be changed in future, in new chips only, in Ice Lake or Cannon Lake chipsets.
of course, if you have good BIOS without mistakes in flash descriptor region settings, and without other vulnerability which can use for rewrite ME region, you will be safety.
In some level safety.
Yeah.
If no one has physical access to your machine.
Yeah. If attacker always can hack to you via physical access. If you don't see on these vectors, it is not problem for you if your vendors have a good BIOS.
But we made many systems and properly configured, actually.
How much time and effort did you put in from start to finish, and was the bounty worth it?
Sorry. It's a difficult question. I don't know. Maybe we'll discuss it after talk.
Have you looked into the interaction between SGX and ME? Especially if you have code execution in ME, can you decrypt the SGX encrypted memory, enclave memory?
It's a good question. We don't know about how SGX relate. We know only some small detail about how GX relate with ME, but we don't investigate it. We will plan do it later. Thank you.
Hi.
Hi.
Is the code of the BUP, was it unencrypted on the flash, or was it compressed with Huffman codes or something like that, or was it just plain?
Oh, sorry, please repeat slowly.
How did you get the binary of the BUP? Was it in plain text on the SPI flash?
Yes, it is compressed by private Huffman code with private tables.
So how did you recover the tables?
Oh, you can read about it in article. You can find the links in my
Just
Twitter.
now published it today.
Today, it's article about it published. Thank you, Dmitry Sklarov.
Thank you.
I saw you activate the JTAG feature access to the CPU, and is it a specific device to connect it or something?
Yeah, there is special device, SVT closed chase adapter.
Called SVT.
Into blue box, small blue box. But it is also possible without this device, but with some restrictions. For example, you can debug management engine early booting stages from reset vector, but except this, you can debug management engine with special USB 3 debug cable.
Oh, so is it public available to buy it?
Yes,
yeah.
you can. It is USB 3 debug cable. It can be bought in special magazines.
You can read about it in our previous talk, tapping into the core, We talked about how you can use DCI for CPU debugging. You can find information about JTAG adapter or USB cable. You can do it themselves. Sorry.
You can construct this cable by self.
Okay, thank you.
So is the exploit, does it depend on the firmware provided by Intel alone, or does it depend on the firmware parts provided by the motherboard manufacturer as well?
No, it
completely depends on Intel firmware.
It only Intel firmware, and they relative only with Intel public key, which signed ME. And if your chips allows to run codes which signed on this key, you always to use our exploit.
All right, thank you. And the other question is, you mentioned that in order to be remotely exploitable, one of the three options was to have AMT enabled. And
not one of three, but all three.
All three.
Yeah,
completely.
All three at the same time. But
yeah.
The first one was to have AMT enabled. And my question is it sufficient to be enabled, or does it have to be fully configured and functional as well, with server and everything?
Yes, you need AMT with network access, of course.
Provisioning.
Provisioning, yeah. Another question. That's all?
That's all. Thank you.